Good evening. We're Team Mizu. Due to the natural disaster that caused the nuclear reactor in Fukushima, Japan, to leak radioactive material into the environment, we have designed a unit process to remove cesium-137 from the contaminated water. Cesium-137 is a radioactive byproduct of nuclear fission that has a half-life of approximately 30 years and decays into barium-137. Cesium-137 is dangerous due to its ability to emit both beta particles and gamma rays. It is able to be ingested through the contamination of water, soil, and air that then comes into contact with the body. Ingestion leads to serious burns, death, and cancer.
To resolve this pertinent issue, we decided to implement an ion exchange operation. Ion exchange is a chemical process by which our wastewater passes through a mineral bed inside a series of columns. This bed is comprised of the bead-like zeolite, naturally occurring ion exchange material that efficiently replaces the radioactive ions with harmless ones, like magnesium, sodium, calcium, and potassium. We came to the conclusion that ion exchange was our unit operation after considering a few other alternatives. Using a byproduct from the paper industry, which naturally removed radioactivity, was of particular interest to us, but due to lack of research on this new discovery, we were unable to continue with it. After deciding on an operation, we had to explore the various methods to implement it. This flowchart shows our two main options, which were a natural mineral or a synthetic resin. After an analysis of the two, we chose the cesium-specific mineral called clinoptilolite.
Our ion exchange system will be installed in an existing wastewater plant. The system will begin with screening and grit removal, followed by primary and secondary sedimentation, aeration, and filtration. Each of these unit operations will remove some portion of the cesium contaminant. However, without specific data on the existing plant, any assumption about their removal efficiency would be pure speculation. So we've assumed an inflow concentration at the ion exchange unit rather than at the plant inflow. We assumed a concentration of 100 becquerels per liter of cesium at our unit inflow. In practice, this number will vary dramatically, but 100 becquerels per liter represents a worst-case scenario. Our unit may be followed by other units to remove other radionuclides such as iodine, uranium, and others. The ion exchange unit will consist of 7 columns, each about 10 meters tall and 3 meters in diameter, connected in series. The ion exchange material fills the columns much like a sand filter. We picked clinoptilolite for our ion exchange material. This is a mineral of the zeolite family. Zeolites in general are very effective at filtration and ion exchange. Clinoptilolite in particular is very selective for cesium. Therefore, it will help remove the cesium thoroughly and avoid premature loading with other ions in the wastewater. Eventually, our clinoptilolite will need to be disposed of, along with radioactive solid waste from other units. While this is beyond the scope of our design, the zeolite would lend itself to disposal by vitrification.
Each ion exchange column consists of 3 major components: a clinoptilolite bed, steel liner, and lead cast. The clinoptilolite, which was previously mentioned, removes the cesium-137. The steel liner is simply a separation between the lead cast and the water moving through the system in order to prevent cross-contamination with the lead and water. The 2-inch lead cast just acts as a barrier to prevent the emission of gamma rays from the process. A rough cost analysis was then conducted from only the materials used and not taking into consideration the installation costs and manpower to set up and run the unit operation. The final material cost was determined to be just over $26 million.
In order to design our unit operation, we needed to find multiple design variables. We used these equations to calculate the necessary parameters needed for our system. We started out our calculations by finding the influent concentrations of cesium-137 along with the required volume of clinoptilolite to remove that cesium through standard stoichiometry. We then also had to consider that our resin needed to account for the massive flow rate entering into each column. We decided to proceed through the rest of the calculations with the larger flow rate. Next, we determined the amount of columns our system was going to have. We accomplished this through finding the total required surface area of clinoptilolite and divided this by the cross-sectional area of each column. Once we knew how many columns our system was going to need, we determined the pressure drop through a single column. This calculation is a check to make sure that our columns would not fail due to too much pressure buildup inside an individual column. We also calculated the adsorption isotherm rate of our resin, which provides us with a way to monitor how effective our system is running. This table shows the results that we based our design of the ion exchange system. As you can see, we found our total amount of clinoptilolite to be 437 cubic meters for a 7-column system that runs at an absorption rate of 5 times 10 to the negative 14th milligrams of cesium per gram of clinoptilolite.
We modeled our operation in Stella. This graph shows the result of the accumulated cesium removal and total treated water. This information shows the efficiency and capacity of our operation over time. Here is a list of sources used in our analysis. Thank you.